But quick announcements. We got a lot of content to go through today. And because of some of this is new and is on your homework, we're going to make a change. Question 3, I was revisiting last night on your homework. I think we're going to make it like a completion. Did you give it a solid attempt, or do you just look at it and throw it out the window? Kind of like participation grade, because I think I underestimated how much time it takes to do singularities on steps, on step shafts. And so we'll have like a mini example, and then I can post the MATLAB code that you would use to go through it. But I think it's not a realistic ask considering the time constraints of this class. But today is the last day of beam bending. We're going to talk about transverse shear, superposition, and using the use of singularity functions for solving for beam deflections. Full disclosure, the first quarter of this lecture is ripped pretty much straight from the Sufficient Engineering video. It's a fantastic video. It's also in the link from last week. And I think it's a really, really good way to get, it has fantastic visuals and a right pace. I highly recommend this entire channel, particularly this video. We're actually going to watch 5 minutes of the next video of another video of his later in the lecture. But oh no, don't do that. There we go. Okay, so when we have a beam under loading, there is a shear, and then there's a moment acting upon the free end, or wherever we make our imaginary cut in the beam. We've went over this. We're gonna really get a good intuition understanding of this. So we're gonna start with pure bending, looking at only the moment. When you have a beam that is in pure bending, there's no shear, there's only moments being applied to it. What you can do is that if you have a uniform bend, so assuming you only have 2 equal moments, equal and opposite on the fixed ends of your beams, you can create, and this is, if you remember how you derive your beam bending and stress formulas and what the assumptions are in this, or you'll get to it next solid soon. This should be somewhat similar, but basically, when you have a beam in pure bending, you can look at this the lines that pass through each section. The center line, or the centroid, which is where you're going to measure your distance from Y whenever you're doing beam stress calculations, that centroid of your beam, when you have a pure bending case, will remain its original length. Any line, and so okay, do we have positive or negative bending in this case? Positive, yes, because our beam deflection is smiling, think positive. So we have a beam in positive bending at this moment. So the lines underneath it, these are going to be underneath your centroid, assuming a standard XY axis, are going to be changing in length and growing. That means they are stretching apart. The bottom half of this beam is in tension. Similarly, if we were to flip this beam around, so we have the same axis here, so take notice that the moments are changing. We're just simply flipping the beam around just to visualize it. The other section here, those center lines, those are going to be shortening in length, and the bottom half of that, or top half, depending on when your top half is, those are going to be in compression. So you want to, especially when you're thinking about okay, which side of the beam is in tension, which side of the beam is in compression. It's a very common interview question, by the way, just real quick. Can you filter out the people? You always want to remember your coordinate system and make sure if you're in positive or negative bending. But when you have this coupling of one section in tension, one section in compression, you are now creating normal stress above and below that line, equal and opposite, creating a force couple. That is where our moment comes from, to get a good solid understanding of why we represent this as a moment acting on the face of the beam. To go back to, we're recognizing that is a moment acting on that face of the beam. How do we go and change that to an actual formula that we can use that represents stress, bending stress? I kind of breezed through this last class. But essentially, if you go look at the, this is looking along the x-axis, we have this top part in compression, this bottom part in the tension. And so that is what creates the moment. And we can use this formula right here. Y being the distance of wherever you are from your centroid or your neutral axis. So that would mean that on my beam, which height of it would have the greatest bending stress? Top, middle, bottom? Yeah, assuming it's completely uneven, it should be equal and opposite on the other side. I do want to point out this negative sign. This negative sign just denotes what your central coordinate system is. So one side of this will be in tension, one side will be in compression. So sometimes you'll see it with the negative sign, sometimes you won't. Just keep that in mind. That's why it sometimes appears, sometimes it doesn't. I is your second moment of inertia. Thank you for the setup. Your second moment of inertia, or your sometimes called your area moment of inertia. It is, I don't really ever remember the full formula for this. I always use to look up tables. I have a link in here in the slides that I'll pull up real fast. I think it's super useful to go through and see these resources that gets a quick explanation for it. If you're looking for the actual formula for it, it's the double integration of how much area is above your centroid line using this formula right here. But truly the most useful thing you need to know is that when you scroll through, you're going to find your most common shapes and pull this formula of whatever you need to use it. Okay. Okay, any questions about the moment and how we get our formula for bending stress? Sick. Let's talk about shear, because shear is something that's kind of like super quickly gone over in mech solids, and it's not given a ton of care and detail. And the fact that, like, I'll be honest, I haven't had to use it in my engineering career so far, but it is a very useful thing to know. And so we want to make sure it's included. So we're going to focus on the shear stress now. The shear stress, when we represented it, there is just a vertical force going on down on that face. And in order for this face to be in equilibrium, for this face, or for these like vertical shear forces going down, if we pull out an individual stress element, there needs to be a complementary horizontal shear stress acting along, like, out of the face as well. Which is a little difficult to think about, but there's a really great way to visualize it. If we go back to the slides we looked at before, when you have something in pure bending, if you had a beam made of several strips, not glued together, they're just strips together. If you put something in pure bending, all of those are going to stay together. However, if you shear downwards on it, you're going to get sliding along those individual layer lines. So, like, I think it's another way to think about it is that shear stress changes the shape of your element, whereas like deviatoric stress, normal stress changes your volume. You can think of this as like, this is going to cause my thing to slide. I'll be fully honest, I don't fully understand the derivation of this and where the formulas come from. They exist. I've looked at them like once or twice and been like, okay, that's a lot of math that I don't know if I really need to know. But it's something to keep in mind for like what stresses you will see in a beam. Here's a quick GIF of, like, you can see it in the real world. If you have several layer lines, like, you're going to have transverse shear that is going to cause your plates to slide as you go. Where this comes into mind. Earlier, I believe it was Rowan. I might be incorrect. Someone asked me about the vertical shear on this entire face, and I said it was the average shear stress divided by A. I was technically not incorrect, but I was perhaps slightly misleading. You can calculate the average shear stress over an entire face of a cutout cross section. Like, that is something you can do. The average shear stress, however, is like, this profile is not a uniform square profile. And so it is not necessarily your most useful information. When you're considering transverse shear, you're going to want to consider, like, where am I having my max shear? And we'll get to like where that's going to be and why you need to take that into consideration. A lot of these formulas are assuming like this vertical shear stress is acting in a purely Y direction. When you have circular cross sections, that's actually not going to be fully true. But when you get to the center line, those will be true in the shear directions. If that's not making super sense, I'll explain it in another slide coming up. Instead, what we want to do is look at the shear stress at individual sections. And the way we do that is with this formula right here, like tau equals VQ over IB. V is just your shear force that you calculate from your shear moment diagrams. Q is your first moment of area. Next slide explains what that is, but it's kind of similar to your moment of inertia. Others also similar to your moment of area. It's just calculus used for calculating rotating something about an axis. And B is your section width for whatever you're using. Your most common shapes you're going to see are going to be like square beams like this, circular beams, maybe an I-beam. This formula is valid for all shapes that you will see for transverse shear. Again, also the derivation of this is not like super helpful in my opinion. I'm just taking this at face value. You don't have to take it at face value. I'd love to be proved wrong. But where that first moment of area comes from is what we care about is if we're looking for the shear stress acting upon this face right here, or like this face in blue, where that first moment of area has come is that I'm going to take the entire area above where my area of interest is. So if this right here is like, I actually only care about this specific thing right here, I'm going to take the area of the face above that, and then I'm going to multiply that by the distance from my axis to the centroid of that area. So there's a link in the lecture slides for this as well. There's also this section note right here. It's sort of similar to your moment of inertia when you're remembering just like what resists how much how much torque it takes to rotate something about a certain angular velocity. It's just a quality that's used for like calculating centroids and other things. But we're going to use the first moment area. And what we do is that that Q right there from that first moment of area, and that I from the second moment of inertia, those are values that are purely derived from the geometry of whatever our face of interest is. So what we can do is that if we calculate or we look up Q for whatever we need to do to get this certain shape for a rectangle, it's pretty simple and easy. And then when you look up our table for I, figure out what is our particular thing that we care about, and we do the same thing. We plug in our values for width and height or whatever, our radius if we're using a circle or something like that. And essentially what we get to is we get to this actually pretty simple formula that represents tau max. Does anyone want to take a stab at why tau max is occurring along the centroid? It's happening about the centroid because that section right there is where the area moment of inertia is going to be the greatest. So you're just going to have the full area over this over the centroid. If to go back a slide, if I were caring about underneath this, I still wouldn't do the distance. I would do the area underneath the line now. So like this section right here says the area above the axis of interest. If you're going underneath your line, like you can consider if I'm making it about this axis, I need to make sure it's rotating about that. So I still wouldn't do above this area. If I cared about this section right here, I would take this area and then I would do this line. If that makes sense. Are there questions around that? Sick. Okay, so this is the formula for max shear stress, max transverse shear stress on a rectangular face. People have already done the math, and these exist on tables and Shigley's and Gear and other textbooks as well. Some of your other most common shapes that you'll see will be for a circular beam. For a circular beam, tau max is just going to be 4V over 3A. So again, it just comes out to a pretty simple ratio between your shear force divided by your area to figure out what that max shear force is going to be. I had mentioned before the circular cross-section. So where this formula in particular makes some assumptions and that needs to be like addressed is that the shear force, and if you look at the force flow, if you do have a circular path like this, it's not going to be straight lines. They are going to radiate out a little bit to get towards that edge. But when you're at your centroid line right here, they are going to be perfectly perpendicular to your axis of interest. So this formula still holds true. And again, if you want, there's second for circular and rectangular, the formula's right there. So different geometries are going to have different and distinct shear stress profiles. The onus is on if you're working with something weird, like maybe not an I joint, but a T channel or something like that, you should look it up. There are plenty of tables that exist for this. But I think the advantage of this is thinking about, okay, well, why do I want this specific geometry and why does it work well? Why are I-beams so common? I-beams are so common because for a limited amount of material, you can get a ton of stiffness because you have these flanges at the top and the bottom, and you still have this section right here, that the web that will carry the majority of the shear force. The flanges up here will carry the majority of the bending moment because they have a distance away from that centroid axis. And they're cheaper and less material than just regular square beams. If you have a regular square beam, it will be stiffer than this, but it's going to be significantly more material. So, yeah, please.
Also, from like a practical standpoint, something that I've been asked before in interviews is like, why choose I-beam? People usually know like painting and rust resistance is pretty easy on I-beams compared to square tubing, and then access to any hardware tooling. Like say if I put bolts to the top of it, I actually can get to them, opposed to if I use square tubing, it's like really hard to get access. So there's both, I guess, the math side and also the practical side.
Something about rust.
It was like rust protecting and painting. Like it's really easy to paint an I-beam, but if I have square tubing, it gets really hard to get on the inside to like stop any rusting of like bare metal.
That's cool. I didn't know that. Thank you. Where's your fun fact, Nathan? Okay. So that was kind of a run through of transverse shear and review of moment. Are there any questions about that? Sound mostly good? Okay, so this next example is something that I just wanted to do like talking it through. You don't actually have to struggle to write everything down. It is on the slides. There are a few things like more circle that are coming up that we'll address very, very soon, but you can just ignore it. So for this question right here, where we're going to bring it all together of like calculating bending stiffness and transverse shear, we have this simple question right here. We have a rod and we have an arm and we have a force going down on this. We're given some values for what the material is, the distances, and we are asked to find what the max stresses and applied stresses at A and B are. Off rip, anyone have a guess for which section will have the highest bending stress, A or B? Start that. A, nice. You want to take a guess why? No? Okay, cool. So just like intuitively, when we look at this problem and before we even do any calculations, when we're wondering about where our max bending stresses will be, we have this arm that goes out here and it's acting purely in the Y direction. Our maximum Y distance from the centroid, because we're just caring about the stresses on like this circle right here. This is considered like our centroid right here, like B and onwards. And so the distance up here will be maximized there. We should have a similar stress on the bottom, like behind where this arm would be, but in the negative direction. So that would be compression versus tension. But because it's my over I for our bending stress formula, we can just intuitively be like, okay, where we're going to have a stress is going to be at this top right here. If you've like ever hung off a bar or something like that and broken something, you'll see that it will break at that top part where it connects to the wall, where it's in tension. Just because ductile materials tend to fail in tension rather than in compression. Similarly, oppositely, kind of like where we're going to go when we're looking for transverse shear, because we are on that centroid right here, our transverse shear should be highest at point B. So like, let's walk through the example real fast. Actually, before I do that, quick reminder, people in mixology will recognize this. I haven't really explicitly talked about it. Shear stresses from torque are a thing. And this next problem just like mentions it and combines them with transverse shear to figure out max shear stress. For stress related to torque, you just have your torque acting upon a point multiplied by C. C is the same thing as Y, like your distance away from your like axis of rotation. And then J is considered like your analog to your second moment of inertia, except this is the polar moment of inertia. You guys will get to this in mech solids. It's like very, very similar form factor to the bending stress formula, but this is just for torque. Similarly, like the sum of torques about a certain angle will be equal to this formula. You guys will get to that. We're not going to go over this class. If you have any questions, ask a question.
Wait, sorry, what is T again?
T is just torque. So like you can, yeah. Like yeah. Okay. So for point A, I should have included the actual free body diagram here. But you guys can pull that up on your slides. Point A was that top part of the bending stress formula. So here is that form factor. So My, so we had 1,000 pounds that acting downward. Our moment arm was 6 inches. And the radius of the circle that it was on, or the diameter was 1.5 inches. So we just take half of that for our Y term right there for the distance from the centroid. For I, you guys will get pretty used to this. The most common way I see for a solid circular beam, what your second moment of inertia will be pi times your diameter to the 4th divided by 64. You do these formulas enough that just kind of becomes second nature, but also you can also totally look it up. It's just as valid. I didn't highlight it right here, but that torque that I mentioned right here, it's the same form factor, TR over J. It's very similar, like the denominator is exactly the same, except now we have the polar moment of inertia on the bottom, which is slightly different than the second moment of inertia, but looks very similar. It is easy to get them confused. Make a quick like note in your head, and also J and I can look very similar just on X. Okay. Ignore this more circle stuff at the bottom. We'll get to that.
So is there therefore no shear stresses that are being produced other than the stuff being produced by the torque?
Yes. So when you have a free surface, here's a piece of chalk. Actually, here, I'm going to go back a few slides. So I said that your average shear acting upon your face, so much, is I realize I had a slide for this, but your average shear acting across your entire face is a valid quantity to calculate. But however, at the free face and top and bottom, your vertical shear stresses must be 0 because your top faces are not going to be in shear. So like this right here is going to be at 0, and this right here is going to be at 0. So like kind of a mental model you can make is that for shear stresses, like your top and bottom are going to be at 0, and your centroid is going to be at its maximum. Whereas for bending stress, at your centroid, you have no distance y from your height of the centroid, so your bending stress will be 0, and at your top and bottom, that's where you're going to have your maximum stress. One's going to be in tension, one's going to be in compression. Does that help? So, okay. Now we're going to point B. So that was the point of the bottom left. I'm just going to pull this out. Point B, we are now going to start caring about that transverse shear. So we still have, that torsion calculation, TR over J. We had that in the previous problem, so we just slapped that in there as well because this that section is still going to be having some torsional shear stress. But now we need to calculate the transverse shear stress. We have a circular profile, really simple. It's just 4/3 times your volume divided by your area, or not volume, your shear force divided by your area. The shear force in this section is just going to be a pure 1,000 pounds from that force acting down. And so we get 0.75 KSI for torsion. When you want to find, and when we get to Moore circle, this will make a little bit more sense. But to find your max shear stress, you then add your transverse shear and your torsional shear together. So for, I think, a few reasons torsional shear or transverse shear isn't super talked about at Olin is that just compare the values. So for our torsional shear, we have 12 KSI versus for our transverse shear, we have 0.75 KSI. Like just order of magnitude, that's already like more than 10 times bigger. But transverse shear is still an object and things will still fail in transverse shear, particularly anisotropic objects like wood. So if you're ever like in a place that has like log cabin or a wooden beam or something like that, if you see a wooden beam and you see cracks right in the middle of the beam, that is from transverse shear. And so like, I think it's important just to mention it, even though like, if you're in a like engineering sense, working entirely with metals, maybe it's not the most important thing for you to keep in mind on, and your bending stress is going to be, so like, for example, if I go back to my bending stress was 18 KSI, significantly higher, but it's still important to keep in mind. And you don't want to be caught off guard, like why the hell am I fitting at the middle of my center? Cool. Yeah, what's up?
So if there's like a point C on the opposite to point B,
Like,
your total shear stress at that point be less than point B because the torsional stress is going up this way, or do they not add?
they should be equal, but opposite. So
Well, for torsion, but not, but he's asking including transverse,
including what?
including the transverse. So if you have the transverse all going down and the torsion going this way and this way.
Oh,
Or
that's a really good
is it
question.
not like right to think that you add them up to get the max, or you just say like, oh, okay, the
So
torsional is max, that's okay.
I think in this case, you can think of the, and this might, I'm not certain. This would be a really good question for Chris Lee, actually. I think in this case, especially now that we're getting soon to talk about Moore circle, you could consider that transverse shear an out of plane shear effect. And because it's going to cause it to want to slide. Let me go back a few slides. I think I saw, do I not have it in here? No, I don't. Damn it. There's another good slide that I can show you instead. If you remind me, when do you have to leave? 9:20? Okay, we have a little bit of time. Actually, it's about 9 o'clock right now. I know people are still waking up. If anyone needs a bio break, this is it for just moment and shear, transverse shear, and we're going to go to beam deflection next. And we want to take like a quick 5-minute bio break. Cool. All right. Did you have a question? Oh, no. Yeah.
Okay. For the transverse shear, I was curious, why do we only look at the area above the
Not the entire area. So
because that isn't a matter of like.
I think it matters because like we're treating the centroid of an object. So I don't have a picture of it, but if you go back and watch the video, there's an example of a T joint or like a T channel instead of an I channel. And that like your centroid is slightly higher. So your stress like is slightly higher and you don't have a symmetric beam now. And so your stress profile isn't fully symmetric along your y-axis. And like the reason we care about the area above the axis of interest is like we're looking for the shear stress at like this line right here. What is this shear stress acting upon this line? And it matters about how much area is above it, or if we're at the bottom, how much area is below it. And so like that's why it's like as it's increasing, and then when you get to your centroid, you have your max value, and then it starts decreasing.
Okay, so if you're below the centroid, you're not still looking at the area above your.
Yes, exactly. Okay. So yeah, that's why this is true if you're carrying like in the positive y direction above your centroid. the video should explicitly say like or below. If you're doing that, you can also look at this. You can also look at this right here, like in the slides for like what else the area moment or first moment of area. Too many words. Okay, I'm gonna do some kind of on the fly stuff right now and find a picture for you, Zeno, that's in some of the other lecture notes. How is this going, by the way? Is like lectures like engaging? I'm not deaf by PowerPoint. Okay.
I did a cheap example. To show it first.
Yeah.
Oh, where'd you add it?
If you refresh slide 17.
Oh, perfect.
And then it shows side by side transfers.
Yeah.
Here.
Oh, yeah, I guess those are two separate things.
Yeah. But to your point, like for a T joint, you're not gonna have a symmetric like stress profile. So that's why like the area moment matters. And then for the stress for the torsion, right here, this is what the Zeno. This is what like stress profiles look like for in torsion. So like I don't think it's incorrect to think that it subtracts from it because, and again, definitely ask Chris Lee because this is above my pay grade. I don't have a pay grade. I don't think it's correct to think you subtract it when it's going on the other side because that vertical shear that's acting there, that vertical shear, in order for that stress element to be in equilibrium, needs that horizontal element, and that horizontal element, like kind of out of plane, is really the stress that we care about and why it's called like transverse along the axis of the beam shear. Another thing to notice is that like when we care about beam bending cases, our beam bending stress is going to be significantly more like important than our transverse shear and our vertical shear. And so like even the beam bending calculations, those are for objects in pure bending, but because like they're small in comparison to the bending stress, we just typically ignore them and say, this is the stress we care about.
Wait, so is the transverse shear what causes like the bending moment?
No, the bending moment is caused by, so you remember, so like if we go back to here, if we have something in bend, like a beam, and we're putting in pure bending, on our axis, above the line or below the line, one's going to be in tension, one's going to be in compression. And so if we then cut that face and look at it through here, the section that's in this top part, that's in compression, it's pushing this way. That section in the bottom is in tension, it's pulling this way. Remember, a force couple is two forces acting in opposite directions, and that creates a moment.
But isn't the transverse shear like in the same direction as those force connectors?
Oh, I see what you mean. Oh, I see that.
There's no force couple, right? Because it's not different on different sides of this of the center.
Yeah.
It's all acting in the same direction.
So yeah, the transverse shear will all be acting in the same direction. So like, if you truly wanted to get like technical with it, I think you could make an argument saying if your transverse shear, like you could subtract from the tension here. My answer to that would be, remember, this is all model, and this is not how it truly is, but it's close enough that we can do some useful stuff with it.
Safety factor.
Plus, there's a huge safety factor in this, yes. So.
But even if acts like you solve
Yes. So the reason you do that is because like pretty soon we're gonna we're gonna go to like do a really quick like 1-day lecture on Morse circle, because that's a good reference for understanding principal stress, which then leads into failure theories. So why things fail and when. Because like in mixed solids, you get your classic like von Mises stress. And then if a lot of people, when they go through FEA, they're just like, oh, I'll use von Mises for everything, for plastics, for carbon fiber, for everything. Von Mises fixes everything. When in actuality, it's only really good for ductile materials. Meanwhile, you can still use principal stress values and solving for different failure theories for what's the word I'm looking for? Brittle. For brittle. Does that help answer? Awesome. Schwanky? Schwanky. I'm gonna sip my coffee. Okay. Colin, missing anything before we go to beam deflection? All right. The second half of this is going to be about solving beam deflection now. And so we'll have a few examples we'll run through together. There on the Canvas page, there is a beam deflection table, and there are 2 MATLAB scripts for using singularity functions I want to go over. And so I'm just going to talk through this. These next few slides are really meant to be used as like, I'm going to go back and look at them. I can talk through them, but I will admit there's a lot of text on the screen. It just has to be there. And you're going to want to like, I'll talk through it. We'll answer questions as they come along, but you're going to have to come back and just stare at this for a little bit of time before it kind of clicks. That's how I used it. And that's why I think it's useful. And like kind of the reason why I was like, okay, I want to teach this class, because sometimes that's not a super thing we get a lot at Olin. To get started with beam deflection, I kind of wanted to start, remember on the first day of class, Colin walked through Chris Lee's model, where for in solid mechanics, you go from load to stress to strain to deflection. And like the different qualities you use to go from one quality to the other is either based on geometry or not transfer functions. This is not controls. Continuity equations? Forget the name of it. Constitutive equations, yes. To material properties there. For beam deflection, we have a similar just kind of mental train of thought, except you're going to derive each time, or if you're moving in the opposite direction, which is still equally as valid, probably even more important to learn, you integrate. So from deflection, we derive, we have a formula for deflection. We take the derivative of that, we get the slope or the radius of curvature for our beam. That slope plus radius of curvature is the same thing for like doing our beam derivations. We draw our origin and see what the curvature is there. We derive that, we get our moment, we derive that, we get our shear, we derive that, we get our loading function. So this slide right here just like bounces out on that. And on the bottom section right here, what this is reminding you is that if you go back and go to those where you derive those formulas from, if you divide by Young's modulus times the second moment of inertia, you get useful quantities that you can use. So this slide right here is kind of like, if you're trying to forget what order to go, this is the slide I go to. So for beam deflections, I have my loading function Q, which is the 4th derivative of my final deflection. I integrate once, I get my shear profile. I integrate once, I get my moment profile. I integrate another time, I get my radius of curvature, and then I integrate one last time, and I finally get what my actual beam deflection looks like. So like this right here, classical just like solving by hand, this is called usually the double integration method, because I don't have to use any calculus to get my shear and moment diagram, but then to go to my slope function and my deflection function, I need to integrate twice. So that's like the classic mech solids way, double integration method. Exactly as I just said. If you want to take your loading function, you can integrate that at your constant of integration, and then rinse and repeat to go until you finally get to your like pure deflection function. Again, these are all for static cases in small deflections, small being, I believe Avery said rule of thumb is like 10% or something like that. I haven't heard that, but like you need to use your judgment of like, okay, I'm using large displacements right now. I need to do some FEA that like does math that I don't truly understand because I can't do this by hand. Your constant C and 1 will be found by your boundary conditions on your shear and moment functions, and your constants 3 and 4 will be by deflection boundary conditions on slope and your slope and the deflection functions. So your most common one, I think this is on the next slide. No, it's not. I lied to you. But like your most common one you're going to use is that if I have a pin joint or I have a like fixed joint or I have some like reaction force at the start of the beam and at the end of the beam, my deflection at that point is 0 because it has a support. It is not moving anything, or we're going to model it that way. All right, getting started with just kind of going through the double integration method. This is classic mech solids. So we have a beam, 2 reaction pin joints. So no moments, just reaction forces, and we have a uniform load over the entire thing. We do our shear moment diagram to get our shear function and our moment function, and we can, right here, we can write out what this is. This is just a straight line going down. If I integrate this, I can get my moment function down at the bottom. Once I have my moment function, I can integrate that one more time. And then multiply that. This is when you rope in your geometry and material properties. So like when you integrate your moment function, you need to bring in both the Young's modulus of whatever material you're using. We're assuming we're doing we're using a uniform linear isotropic material and our section modulus. At the end of the slide, you can use different section modulus if you have step shaft or a shaft that like changes profile, but it gets a little complicated. So just bear with me for that. I then integrate that one more time, and I now have my Y of just pure deflection. So if I divide by E and I right here, I have a formula that I need to use boundary conditions for to get what my pure deflection is. As I said before, boundary conditions that you're most commonly going to use, especially when you have a pin joint or a fixed joint, you're going to say the deflection at 0 at the start of the beam and the deflection at x equals L at the end of beam equals 0. So you sub in zeros for where your x is right here. C2 comes out to be 0. C1 comes out to be your load value times your length to the third divided by 24. Like this just comes with practice and looking at it. And like I said, there's a lot of text on the slide. You need to just kind of like look at it, think over it, mull it, and figure out, okay, where did that X disappear? Why is that there? Yada, yada, yada. So then once I have my constants for C1 and C2, I plug those in. I now have a formula that I can use for figuring out my deflection when I have a uniform case. This is valid for like any length L. As long as it's still small deflection, as well as my radius of curvature right here. Sometimes you'll see radius of curvature described as theta. If I wanted to go even more step there and figure out where my maximum slope and maximum deflection is, for a simple case like this, I can kind of just use intuition and be like, okay, so I have an entire, I have a loaded joint here. It's going to sag the most in the middle of the beam, so my largest deflection will be there. Meanwhile, my maximum radius of curvature is going to be at the ends of the beams. You can also totally use calculus, remember your mins maximums, to find out where your maximum deflection is going to be. So the previous example and the methodology really only works with a simple beam with one loading condition that's continuous. Like there's no, like the entire shear profile is like a constant function. When I'm doing stuff by hand, that's kind of the limit of what I can do. However, there are more ways that you can do this and integrate or solve either numerically or by hand. And these are some of them. So superposition, moment and area method, singularity functions, numerical methods, and then those are all just like, those are still calculus based. There's 2 methods that are energy based. Castigliano is how you butcher saying that. I don't know how you say it. What? Which is using an energy method. I learned it once, thought it was really confusing. I wasn't down with it, so I didn't want to teach it. And then, of course, you can just use it, plug it into FEA, but of course, that kind of comes with its own bag of tricks of things you need to keep in mind of. In this class, I find superposition to be super helpful, and I find singularity functions to be super helpful. Superposition is kind of the most intuitive, and then singularity functions are like intuitive and makes sense on paper, but then it is the transfer of doing that numerically in MATLAB, or you technically can't do it by hand, but it sounds like hell. Which a lot of people find struggle with, myself included, which is why the last question on your homework too, we're just going to make it like, try your best, write down something, write down your confusions or where things go wrong, and we'll help you out. The next thing I want to do is, oh wait, shit. Okay. You guys want to watch a video first that goes over both superposition and singularity functions, or have me talk through singularity functions, have it reinforced by the video, and then go into singularity? They both start with S. Video first? Yay! Okay, it's because it's a fun video. Okay. Because I am a hack and have no true skill, I am stealing from Efficient Engineer one more time. This entire video, sublime, beautiful. I love it. I would give my firstborn child to this channel. Okay, so we're gonna start. Singularity functions are also sometimes called Macaulay's method, and then superposition is gonna be next. Okay. Wow. Where's my audio?
You're also at full volume.
Do I have to plug in the aux cord? I feel like I shouldn't have to over USB-C. Nathan, can I see your computer? Oh, yeah. And then go to like 8:30. Deflection of beams. It worked. Oh, wake up, Jeff. Beans
in a whole range of different. It's important for engineers to solve a system of equations, complicates things, and makes it more difficult of the beam, particularly for cases where the beam needs to be split into a large number of sections. Fortunately, there's a powerful mathematical trick that allows us to define a bending moment profile like this one using a single double integration. Profile like this one using a single expression so that we can apply the double integration method without having to split the beam. It uses singularity functions to make solving this type of beam much easier. They are defined using this special notation and follow specific rules. When the expression inside the bracket gives a positive number, the output is the expression, but when it is negative, the output is 0. These are called Macaulay brackets. and applying them to calculate the deflection of beams is called Macaulay's method. Their behavior allows us to essentially turn different terms in the bending moment equation on and off as we move along a beam. We can work through the beam we looked at earlier to understand how. Let's see how the bending moment changes as we move along the beam. In the first half of the beam, only the reaction force contributes to the bending moment, and the moment arm is equal to x. But once we get past halfway, we need to include the effect of the concentrated load as well. And so the bending moment expression has to include an additional term. The moment arm is equal to x minus half the length of the beam. If we replace the brackets in this expression with Macaulay brackets, the second term in the expression will be switched off in the first half of the beam, since x minus L over 2 will give a negative number. And so this expression, using Macaulay brackets, defines the bending moment along the entire length of the beam. The same thing works for distributed loads, although it's slightly different. When using Macaulay brackets for a uniformly distributed load, the bracket has to appear twice, once in the magnitude of the load and once in the moment arm. The moment arm is the distance to the center of the distributed load, so is equal to the length over which the load is applied, divided by 2. And so we get this expression, where the Macaulay bracket is squared and the distributed load is divided by 2. This expression is only valid if the distributed load extends all the way to the end of the beam. If it doesn't, we have to adjust the expression to balance the part of the load that's missing.
So kind of confusing, doesn't go super into details there. What he's doing right now is that if you're pretending that like your load is actually only for like the third quarter of on your beam, and when you're using singularity functions, you have to include a second term that negates the fact of that after the beam. And the way you do that is that you change where your moment arm is acting upon. So you have this section half here and this section half here that effectively cancel each other out. And that's what makes it only act on this part.
Here's how you can apply Macaulay brackets for a few other load types.
And these are written in your notes, so don't feel super stressed to like write it out. You'll notice for each new ramp or whatever, you're increasing once in your exponent.
Macaulay brackets also have special rules for integration. They are integrated in a similar way to polynomial functions, like this, which makes it easy to apply the double integration method when using them. Let's go back to our beam with a concentrated load and solve the deflections using Macaulay's method. Since we have a single expression that defines M along the full length of the beam, we no longer need to split the beam into sections to solve it, and we can just apply the double integration method as we normally would. The double integration method can be quite time-consuming to apply, even when using Macaulay's method. To save us from having to go through the integration process every time we want to calculate the deflection of a beam, reference texts often include tables which list the deflection equations for a set of typical load and support configurations. This is more powerful than it might seem at first glance, because the principle of superposition can be used to apply this small set of solutions to a much wider range of problems. It allows us to combine different load configurations on top of one another, and to calculate the overall deflection caused by the combined loading by summing up the contribution of each load to the total deflection. This is a really powerful technique that's not just used for the analysis of beams, but also more widely in structural analysis. For the superposition method to be applicable, deflections must vary linearly with the applied loads. And deflections need to be small, since large deflections could mean that the applied loads don't act independently. Sometimes when analyzing a beam, we might only be
Okay, so great video. Love this channel. Was the escape key on the touch bar? Whoa. Mac moment. So that's just kind of like a visual method for what we're about to do. We're now going to work through a few problems using both singularity functions and superposition, starting with superposition, because I think it's a bit easier to get like your head around. If you guys go to your Canvas page for today, there's a lot of links in there. One of them is a table, a reference text of simple load conditions. So why don't I pull that up actually? So if I go to my beam bending tables right here, these texts, you're going to see them like there's a full 8 pages of them, and they have like almost every condition you can even possibly think of labeled out. And for each one, they're going to include what the reaction forces are going to be, and put them in terms where like you can change where your you can change the length of where your force load is applied. They're going to include shear moment diagrams for what they look like. They're super, super, super useful. And like you guys should definitely keep these in your back pocket and know that they exist, because again, like if you have superposition and you have a loading condition where you think you can neglect having to go through double integration method, it saves so much time and gives you a good answer. Going back here. So this right here is a prime example of that, and similar to the one that was in the video. We just essentially have our top right is our loading condition. What we have is a pin-pin joint with a force couple, a point force somewhere along the length of the beam. And then we are superimposing that on top of a beam that just has a uniform load across the entire length. As stated in the video, why is it shaking so much?
It's like a machine.
Yeah. Whoa. It's that excited for superposition. So each effect must be linearly related to the deflection it produces. So like you have to be in the linear elastic range. Doesn't condition that dramatically changes the effect of another load. So if you have one force that has super, super big. And again, like there's no hard guidelines on this. You just have to use your judgment. And then if you're confused or worried, I would back up using another method to see if you get similar answers, either with FEA or something like that. So here's your loading condition. On the left side, you have your intermediate load. You solve for that just doing a sum of moments about each reaction joint, and you get a shear moment diagram that looks something like this. And we, in the previous example, already did an example where we have solve for the reaction loads of a uniform load across the entire bridge or a beam. And so we can take our moment and our moment function, our deflection function, and our max deflections. From there, if we want to double integrate after that, we still can. Otherwise, on this one, a specific example, they go through the double integration method just to show how you can go from your moment and deflection. But if you go to your reference text, they already have your deflection of there. But if you want to do it by hand, it exists. The only thing you need to do is that when you have a combined loading case, you need to remember that like at your boundary condition where you go, your deflection before the point load and after the point load are going to be equal to each other. So you kind of use the left and the right method of that, and also same thing with your radius of curvature. All right. Basically, if you take your deflection of all this, like on this left side, it's taking the deflection from A to B. On the right side, it's taking the deflection from B to C. It's setting them equal back to each other, integrating twice to get your constant integration, and then summing those back into the formula. If you go through just the like table method, you're gonna start with just these formulas here, and get to and get to like what your total deflection is. So on the right side, you have more kind of an even distributed function where it doesn't matter where your point load is, versus with your deflection on one side, it matters where A and B are. So what you do is that you take your reaction loads, you add them together. So R1 is here, R1 is here. Add those two together for your reaction loads at A, add those two together for your reaction loads at C. And then what you do is you just take your deflection from A to B from your first equation right here. You add that to your deflection that you would get from A to B there. And you do the same exact thing from B to C. Very kind of like super fast resolution. I'm seeing that look in your face. Yeah. You want to go through it again? Or okay. For what it's worth, we don't ask you to do this in your homework. Like just because it's useful to know that this exists, and it's pretty simple to just like put it together in a more compact, like readable way than all this text on the slide, but it's just useful to do that. Singularity functions, yay! Okay. In the video, singularity functions are useful because the brackets give you a way to turn off the effect if it's no longer required or it's not. This table right here gives you like what power of exponent you use when you have an applied like something. So right here you have applied moment, that's to the negative 2. You integrate that once. I also like this because it gives you like your integration method, and it just follows the simple power rule. Actually, well, no, it doesn't follow the power rule for here because you don't have 1 over -2. You go from that to a concentrated force, like a unit impulse. Integrate that, you get to a unit step. So this would be for a distributed load, and then integrate that, and you get to a ramp. And so this would be for a ramping up load. These are super powerful and useful because you can turn them off. Like you don't need to do it by hand and solve by everything, and you can just force it for MATLAB to do it. Kind of back at this section right here, I threw this video in. It's a 3-minute video that shows you how to actually type it in MATLAB. And on top of that, you also have a script that will help you do that. But for the pseudocode is that if the value inside my bracket is a negative number, like the absolute value of it, the magnitude is just canceled out, it goes to 0. If inside my brackets, I have a positive value, it's equal to whatever value is inside that bracket. So it's still like X minus whatever your distance is. So you can figure out what your moment arm is for how long you're going across. Oh no, don't do that.
Thanks.
Oh geez. Well, now the video. Okay. Of course. This is our first example. If you go to your Canvas page, the first question should be singularity functions example 1 or something like that. Why don't we have everyone pull that up? Because we just have a simple beam load here, and we have a unit step distributed load that starts at 4 meters and goes all the way to the end of the beam.
It's supposed to be just a MATLAB script.
Yeah, it should be posted, right? On the day page. Yeah? Okay, sick. So this is the first example. Can everyone read that? That looks really tiny. Oh, okay. Let's do this.
If you hold control and then like scroll.
That's not seeming to be too happy either. MATLAB, do what I want you to. Zoom. That's unfortunate. I don't want that. It's that's not seeming to want to work.
Control and then 2 fingers scroll.
It might be, well, so what I do is, because I got tired of lugging my laptop around everywhere, is that I keep my computer in my room and then I remote into it. And so this might be because I'm using Parsec.
I haven't pulled up this.
Go for it. Where is the technology? Thank you, Colin. Okay. Do you have the slides pulled up too?
Yes.
Sick.
Should be.
Is it just Command Tab to switch between windows? Does that work? Nope.
It is command.
Okay. Oh geez. There it is.
Doesn't work on that, but
Isn't technology great, y'all? Okay. Okay. You guys might have to duck between. Yeah, that's just not useful at all. All right, we're just gonna do it this way. So in this script, really the only thing to point out that of usefulness is when you are applying a moment or applying like a singularity function, the way that you do it is that like the actual what would go in brackets, you replace with, instead of like x minus 0 or x minus 4, you do x greater than whatever your value is for your moment arm. And you need to do element wise like dot multiply. So like, for example, going back here, if I go to the actual condition right here, I have my shear function right here. So like what I would do is that what I typically do is by hand, I write out my loading condition, which is right here. So my first reaction force up until 4 meters, like the only shear force or the only load that's occurring on the beam is from this reaction pin right here, which is just a unit impulse force. On my chart to my left right here, I see that to activate it, it's just like the brackets minus whatever distance it's going to the -1 power. So I go over there. When I get to 4 meters, I now have a distributed load that goes across to the end of the beam. So that's great because I don't have to worry about adding an additional term that would turn it off if the distributed load ended any sooner. For the distributed load, I take the value of whatever the like force distribution is, so 10 newtons per meter, and then I multiply that by the unit step function I have here, where it's x minus whatever your value is to the 0th power. And finally, I have one more final unit impulse at the end of the beam. That's just my second reaction force, same way that I implemented it here. I usually write this out by hand. I usually don't put this in MATLAB because it can kind of get confusing and get really long lengths and text of code. After that, I integrate like using by hand to go up to the what my shear function will look like. So luckily right here, you have the same, like it gives you the rules of integration right here, which is super helpful. You really don't need to notice it until the ramp function, and then it just kind of obeys the power rule where you put the like whatever you're raising your exponent to, throw that in your denominator as well. So v equals r1 x to the 0th power minus w times x minus 4 to the 1st power plus r2 times x to the 2nd to the 0th power. In this condition right here, they're still solving it by hand, and including a boundary condition right there. The boundary condition is that where x equals 0, or when x equals 0, the shear force there is going to equal 0. So your first constant of integration is going to be equal 0. You don't really need to worry about that with the singularity function at this moment in time, because we don't need to, not going to there. So to go from this equation right here, where I wanted to turn on like all the time, I just have my R1 force dot like element multiply x to the greater than 0 in just standard brackets. So that's fine right there. When I want to include my unit function or my unit step function for my distributed load, I now have this to the first power. And so to make that work to where it's actually to the first power, I first take I take my distributed load and I multiply it by my moment arm here. And then this unit right here is what turns it on in MATLAB. That video in the slide kind of explains this super quickly, and you can replay and go back. But like this right here counts as my moment arm. This right here is what kind of counts as my what's in my like angle brackets. And similarly, this is the same thing there. So then when I go to integrate it, to get to my moment, I now have a second moment arm that comes in here. So I just multiply this x, but before I multiply by here. In this case, I didn't choose to do to the second power just because I wanted to reiterate, you bring in another moment arm that comes in here. And then because this right here was a unit step function, and now I'm integrating it to get there, I have to divide by 2, according to this chart. And then the reaction force right there is exactly the same. So I have this, I'll go ahead and run it. And immediately I have my shear force diagram. Where's Chrome? Oh. Colin, how do I bring my tab over so that this is overlays on top of the Chrome?
You pull it up, like the hotbar, and then like.
There we go. And so here's my shear function, here's my moment function. If I go through and look at the actual values, they match up. If I wanted to take this a step further and go to both the radius of curvature and the deflection, all I need to do is repeat that process of where I went from where I integrated. I am not Mac pilled.
It's confusing to see MATLAB open. On it.
Oh, okay, so
Swipe over again. The green finger swipe to your left.
yay. If I wanted to go to my radius of curvature, I integrate this entire feature one more time, following the integration rules. And then what I'm going to do is divide that by my geometry, the polar moment of inertia, second moment of inertia, and the Young's modulus. So
Is that just like a rule, or does that come from the integration somewhere?
So that comes not from the integrate. That doesn't come from like a rule. That comes from like when you are deriving your like your formulas for bending stress and going from radius of curvature. Like you'll have your moment divided by your radius of curvature is equal to. Oh, I'm shooting from the hip right now. No, 1 over your, sometimes you see it as rho, like your radius of curvature. I'm like 80% sure that's correct. And if it's wrong, I'll send a Canvas announcement after that. But when you are going back and doing the derivation of like where we get all these beam bending and assumptions from, you get something that looks like this. And so the divided by e to the I is what you care about. So that's why like when I'm always trying to remember, okay, where I actually care for my functions, this slide in particular is what I go to.
So if we were to integrate the moment one more time, you would have to remember to just divide it
Yeah. So, because so if you notice right here, you look at the axes, the axes include e to the I, in these equations. So if I were to, or in these functions, so I need to divide by that to get to the actual like real function we're looking at. And also you'll notice like, if you forget to do it, you'll notice it real fast because all of a sudden it'll say your beam's deflecting by like 900,000 like millimeters. You're like, oh shit, I need to divide by the Young's modulus, because that's where the biggest change in like order of magnitude is going to come from. Because like for most of these, you're going to be using steel, which is like 200 gigapascals. So you're going to be off by a huge factor, and that'll be a big cue to you. Fuck, I forgot to divide it by E and forgot to divide by I.
But going the other way, you multiply by yeah.
Yes, but it's going to be a very rare case where you start with your deflection and you need to get to, okay, what's the moment in shear in this? Which is why I think, yeah.
So you divide by EI once when you're integrating from the moment to the radius of curvature.
Yeah, and then you don't have to divide it like, well, so you divide, but you need it in the deflection function as well. Like you don't divide again, but you divide once and that carries through.
Right, yeah.
Okay. So with the tools y'all have now, there is a second singularity function right here. If you guys want to take a chance and crack at writing this out and seeing if you get a similar shear moment diagram. If not, you can just skip straight ahead to so the code for this particular example is already on the page as well. I think it's useful to get this. The homework has one just shear moment diagram using that using that shaft that has 2 pulleys on it from your previous homework. So you just need to take that and make a moment shear diagram, note where the max bending moment is. Question 2 is a cantilever beam with uniform load. It asks for singularity functions. If you want to use superposition, like it looks something like this. And I think there might be like one more point load or something like that. It asks for you to solve for the deflection of this. The homework explicitly says singularity functions. If you want to take a crack at this using superposition, that's totally fine. I can change the language on that as well. Third homework question has a stepped shaft example where you have changing second moments of inertia. And it asks you to use it using singularity function. And it's a bitch. So for that one, you guys are just learning this. I don't think it's entirely fair to ask to have you slog through that for a 2-credit class. So if you want to take a look at it and like struggle through it for a little bit, totally fair. And I encourage you to do that. But I think we're going to make that just kind of like give it some attempt. Because the thing with that function, and in the last like 5 minutes of class, I'll go through like a special step you need to make, because you'll have a discrete jump in your like m divided by EI. You'll have a discrete jump where you are changing the diameter of your shaft, and you have to include that using a singularity step function. So for the meantime, why don't you try just solving for this and see if you can match your match the shear moment diagram that's already on the slides. And if not, we can come around. What's up? So sorry, yeah, on this is kind of drawn really weird. There's a fixed joint on the right side and it's a free joint on the left. So like I think it's more you could solve it either way, truthfully. I do think it's kind of more convenient to do it this way, because if you do it this way, this distributed load goes to the end of the beam and you don't have to turn it off and add a second thing in. So like that's another tool you can have up your trick, is that you can just flip it around of which direction it is and you'll get the same results. A good way to double check that your your singularity functions are working is that if you look at your moment diagram, you should start and end at 0. If you're not, something's wrong. Oh, do you want your laptop back? Okay.
Yeah, you're right, that's a moment curvature.
It is? Oh, let's go. Thank you, Emily. I'm going to go ahead and make the Canvas announcement about homework 3 or question 3 on the homework. just eye on the clock. Does anyone have any questions or anything right now?
Quickly, like, so with the whole like power singularity function, when it's telling us like that this one is negative, this is negative one. That's saying the load is negative.
That's so, yeah. That's saying, so what you would do is you take the magnitude of whatever your force is and then multiply it by this function.
No, I totally understand that, like, but for like, when I write it with V, that's already after the instead of integration, right?
Yes, so yeah, you're correct. This is the load. This is
Okay.
how you write out your load function. That's a very good question. So you write out these powers to the integration or powers of the exponent. That's with your load function. So that's why I write out my load function first, just on paper,
Okay,
and then I integrate it once to get my shear.
and then another, okay, cool. Sure.
Okay, thank you so much. Okay, I just sent out the Canvas announcement, but I do have some slides that go over the step shaft. We're definitely not gonna have time to like fully discuss it, maybe not fully understand it, but I just want to do diligence and like mention how you would do it. If you go to the next few slides here for the second singularity question function, there is like the written out if you wanted to do it by hand and just see it how they did it there. And then there's also the code posted online and it matches the moment shear diagram that you're given. So should be all good.
For clarification, when we're doing singularity functions, we only need to go to like setting up the group, right? And then we can go to that level.
Yes. Yes. Okay. So these next three slides are about using singularity functions on step shafts. Step shafts are tricky because you like out of nowhere have a sudden change in your moment divided by your Young modulus and second moment inertia. And so the way that you accomplish this is that it's same as you write it out, like your moment across the entire diagram will be the same because that is not dependent on the geometry of your function. It's only dependent on your loading conditions. But the actual value of like how much that'll lead to the deflection and going back to your radius of curvature equation of where this comes from, you then have a sudden discrete like jump. So the way that you accomplish this is kind of a little backwards. You have to sketch out your shear moment diagram, which you can do regardless from the get-go because that doesn't depend on geometry. And then you kind of have to like work a little backwards and plug it into singularity functions. So what I mean by that is write it out like you would solve for any other function. And then when you want to account for a drop in the moment divided by your second inertia, technically there should be an E in here as well, but we're just kind of ignoring that right now. You want to add a step term that accounts for the drop in and below. So what I do is that I look at what is my value of M divided by EI to the left of this piece, like just before the jump, and immediately to the right of this piece just after the jump. And I write that down, and whatever the difference between those two is how much I need to like, similarly to how you throw in an extra term to cancel out a distributed load that doesn't go to the end, you need to throw in an additional term that jumps to it, adds a discrete jump to it. The second thing you need to do then, which is a little confusing, so like you have to add an additional step term, is that you need to then look at for the moment, you need to add an additional ramp term that like accounts for the slope of what that section would be. So where's my pen? So if I have some graph like this, and I'm going to call this A, B, and C. The way I would do this is that, I mean, I'm going to have just some load here. The way that I would do this is that I would start with, okay, this section right here is going to be my moment divided by the whatever my second moment of inertia, or whatever the value of like I get from my geometry here, and I want to look that to the left, and I want to look at it to the right, and then I write that down. So I usually do like left, B, right, and then I do that calculation by hand because I have my moment, I have my values, I can just write it out. So say that this is like 30, say this is like 50, I can do 15, say this is like 10. I then subtract those two from right to left to figure out what my jump down is going to be. So in this case, it'd be -20. That is my step function that gets added into here. That accounts for the straight jump down. The next thing I do is I look at what, so now I'm done with this part. I look at my second moment here, and I look at what slope this point needs to get to whatever this next section would be there, because that's an additional like ramp function of the additional slope that's incurred that needs to be added to match what goes on here. Because the problem is that when you have a single geometry, it only accounts for when you do m divided by ei. It only accounts for that single I. You need to then account for like the entire function, like mi1 plus m over i2, and so on and so on and so on. And so what that additional step function does, a ramp function is, that does the slope of like right here, I would look at what my m over ei is, and I would look at my m over ei is, and I would figure out the slope that adds to there, and I add that ramp function. It's like 10-10 on the dot. Want to be respectful of y'all's time. This is why I just kind of skip over or just glance over this, the last question on the homework. It's not going to be graded for correctness or anything like that. Just make a genuine like attempt to like write down what makes sense, or pay me for office hours. Yay! You guys are great. I'm shutting up next week. I'm not lecturing, so you don't have to talk. You don't have to listen to me anymore. What's up? Probably most likely outcome is that we'll just get already go together and like together to show like what is complete. What's our lectures in? Yeah, that's how I was feeling. And I was like, we need to do more class examples, like for everyone together. Yeah.
Yeah, I would like literally stack.
That was true. Someone gave feedback yesterday that, or last week, last class, that for future reference, I'm going to include, if you go through your textbook and see what chapter this is, just skim over it. That'll be at the end of the slide. So, so I'm going to add that right now.
Thank you.
You guys are great. Ooh. Very nice.